Welcome everyone to this month's edition of the ReproNim webinar. We are super delighted to be joined today by Eugenio Iglesias from Mass General Harvard Medical School. Eugenio has degrees, master's degrees in telecom and electrical engineering from the University of Seville and the Royal Institute of Technology in Sweden. His PhD is in biomedical engineering at UCLA. And he has done postdoctoral work at Martina Center at MGH and the Basque Center for Brain and Language, and now has dual positions, as best I can tell, both at the Martina Center and at University College London. So we're super excited about his work, both in clinical applications and technology development and machine learning and all sorts of cool things that relate to some of the collaborative projects that are related to ReproNim. So without further ado, I will turn the floor over to you.
Thank you very much, David, for the invitation and the kind introduction. My name is Eugenio Iglesias, and I'm going to be talking about this family of methods that we have that we are calling Synth stuff. There's a bunch of them. That's why I have the Synth star here. And they're essentially based on a family of techniques called domain randomization, which are popular in robotics. But it turns out that it's working really well in brain image analysis, enabling using deep learning tools out of the box with any data set, which is, I think, I'd like to make the point, very interesting towards reproducibility. Oops, let's see. There you go. So I'm going to base most of this talk on Synth, which is one of these algorithms I was talking about. But the model that we use is very similar for all of them. So I'll spend most of the time on Synth, and then I will quickly go over Synth-SR, which is the one we have for super resolution. But again, it'll be very easy to introduce once we've discussed Synth first. So let's get started with the motivation. We're all, I think, familiar with the problem of image segmentation. You give me an MRI scan like this, and I want to get labels like that for shape analysis, volumetry, whatever you want to do with it. It's a very important prerequisite for a whole variety of analysis, right? And everything is easy, or I wouldn't say easy, but everything is sort of solved when you talk about research-grade scans, like a 1 millimeter isotropic MPRH that we acquire in any prospective study in research. But when you talk about clinical acquisitions, then things are substantially harder, right? And as far as I know, there is no available package. Like you can get this guy upstairs with FreeSurfer, right, automatically. But for a clinical acquisition like this, how would you get to, a label map that looks like that? So this is tough, mostly because of the variability in the brain scans that you find, say, in the packs of MGH, of Harvard Hospital. You have a lot of variability in contrast. So you've got different type of, pull sequences. We're all familiar with this, T1, T2, proton density, and so forth. Let me call this, if I'm allowed, MR modalities. I know it's all MR, but let me call it modalities if you don't mind. And then within the same modality, you can have a lot of different flavors of contrasts, right? Even within the same sequence, even if it's MP ranges, right? You vary the parameters, you vary the scanner, and you get a whole different flavor of contrasts and brightnesses and details, right? You can also have variability in the preprocessing. Maybe you have a scholar strip data. And of course, the other big factor here is the resolution. And by resolution, I'm going to imply a bunch of several things. First of all, the orientation of the acquisition, which could be axial, coronal, sagittal, or even oblique. The slice spacing. So this is simulated, but I'm taking the same brain and pretending that it was acquired with 3 millimeter axial spacing, 5 or 7 mil. So you see the resolution going down. But there's also the slice thickness, which is normally, it's correlated with the spacing, but it's not a direct correspondence, right? Like these 3 images here have the same slice spacing, but they have different slice thickness. So you can see that they have different levels of blurriness because of that. Of course, the slice thickness introduces our beloved, I should say, partial volume problem, the partial volume effect. I'm zooming in this area of this sagittal slice here, pretending that it was acquired with this coronal acquisition. So you go from this pretty 1 millimeter isotropic voxels to these French fries that you see here on the right. And the problem here, of course, is that if I focus, for example, on this area between two tissue types, CSF and white matter, what happens here is that I end up with a voxel, this French fry that looks neither black nor white, right? It looks like something between. And annoyingly, it looks quite a lot like, for example, this voxel down here, which is a completely different brain region. So this is pretty problematic. So yeah, we would love to have segmentation tools that can deal with this ginormous mess, right? Which we currently, I would argue, do not. And the main application I see for this is, oops, there you go. First of all, is being able to look back into massive amounts of retrospective data we have in the packs already. And second of all, well, if you can analyze this data like accurately, then you can start thinking of more quantitative morphometry in the clinic, right? Without having to require 1 millimeter NP ranges, which is what happens today. So as you can imagine, we are not the first people working on this. So what people are doing these days for every segmentation problem is the supervised convolutional neural networks. And if you have trained data, I would argue everything works. Like, for example, you could learn how to segment this axial 1 millimeter T1s at isotropic 1 millimeter resolution, right? Like you train a supervised network to do this and it will work. Problem, of course, being if you take that network and you apply it to T1 data with a different resolution, it falls apart very quickly, right? Let alone if you change the contrast from T1 to T2. So, I mean, nobody is going to stop you from training different networks to do this. You can have as many networks as you want. The problem is that, well, first of all, you're going to require supervised label data for every target domain. And this is like a nightmare to deploy because like how many networks can you have, right? And there's always going to be like a slightly different acquisition in some study that is going to make your method fail. And even if you have like 1 trillion networks for every possible acquisition you can think of, sometimes selecting the correct network can be hard. DICOM headers are not always reliable. The parameters can be different and so forth. So wouldn't it be cool if we just had like one network that worked for everything, right? This is the goal that we're trying to achieve. People have tried some things to mitigate this problem, mostly based on domain adaptation. So one way of doing this is doing unsupervised domain adaptation, where you say, okay, I have a network that I trained for a source domain, say like 1 millimeter T1 scans. And now I have a target domain, T, which is, for example, 5 millimeter flares or something. So if you give me a bunch of 5 millimeter flares, I can use, for example, this super popular cycle-GAN model, which is unsupervised, to learn how to translate one modality into the other. I don't know if you're familiar with the original paper that was turning horses into zebras. They were also turning, I think, photographs into Monet paintings or Van Goghs and stuff. But the idea is pretty simple. You have like two translator machines, one that goes from the source domain to the target domain, and one that goes the other way around. And the idea is that if you start from, say, a horse, or let's say a T1, you push it through this network that translates into a T2 or a zebra, and then you translate it back and get a double fake T1 or a double fake horse. It should look like the original T1. And same thing the other way around. And once you've done that, what you can do is to take your T1s, make them look like T2s, and train your network. And then you can get a network for T2s for free, so to speak. This requires, I mean, you have to have access to scans from the modality in advance. It not always works that well, and it's not very practical, right? Another option that is a bit more practical in terms of like getting a new scan and being able to analyze it out of the box is test time adaptation. And the idea is that if you have again, a network that you train on, say, 1 millimeter T1 scans, and you also train a denoising autoencoder that essentially learns to go from topologically incorrect segmentations to topologically correct segmentations like this. Something that you can do is to say, okay, if I start from a T2 or any other scan that is not a T1, I segment and I get garbage. What I can do is to push the segmentation through my denoising autoencoder, and then I can provide feedback all the way back here, right? To wiggle like this network, wiggle the weights of this network until I get a segmentation that looks plausible according to the denoising autoencoder. And this works okay. It depends on how big of a domain gap you're trying to close. But it still has the problem that you have to fine-tune a network at test time. So it's not always very practical. And again, it doesn't always work. If you look into the contrast issue, if we forget resolution for a minute, right? Bayesian segmentation has been around forever. This is what like SPM uses, right? Or we have a tool in FreeSurfer called SAMSEG that does this. And the idea is that you build on a generative model that goes from a segmentation to images. And this is just a simple dummy Gaussian mixture model condition on the segmentation. And within this model, you can use Bayesian inference to say, well, if you give me an image, what's the most likely segmentation that generated this, right? And then, because this Gaussian mixture model has parameters that you learn directly from the test scan, if you give me a T2 instead of a T1, it's going to work equally well. So it's completely agnostic to the contrast of the image. Now you could say, well, can you deal with partial voluming? Can you deal with resolution? And in principle, yes. So I can take my generative model and add an extra step that says, take your like fine 1 millimeter isotropic Gaussian mixture model and simulate an acquisition with a prescribed thickness and spacing. Of course, like funnily enough, this looks more realistic than this with the blurring, which is not surprising, maybe. And then you can play the same game and say, hey, can you do inference? It's just Bayesian inference, right? Why cannot you do it? And then go back to a 1 by 1 by 1 segmentation from this guy. And you can do, I mean, it's not impossible. You can do it, right? Writing down the equations is very easy. Even coding the code is very easy, like writing the computer code. The problem is that this is like a very, very complex problem. And the reason is that if you think of this French fry that you have here, this thick slice, at 1 millimeter isotropic, right? This is the average of, for example, 4 or 5 voxels like this. And the problem is that when you think about like how this segmentation generated this image, you have to consider all the possible internal configurations of sub-voxels of this super voxel that gave rise to my to my French fry. And so that quickly becomes computationally intractable. It's not even, I mean, you can write it down, but it would take the age of the universe. My former supervisor, Kungan Input, has a paper on this, and he makes all these approximations, but I don't think anybody has gotten this to work in practice in reasonable times. So it seems like you have CNNs versus Bayesian. The supervised CNNs have advantages. They're fast. They're super accurate on the training domain. Like you train on 1 millimeter T1s, you test on 1 millimeter T1s, and they're amazing. But of course, they're very fragile to this domain gap problem. And Bayesian segmentation is the other way around. You have a pretty good forward model that is contrast adaptive and technically supports partial volume modeling, but it's essentially unusable with PV. So it's not really appropriate for clinical data sets. So our idea is, can we solve this by synthesizing data? Like, can we generate scans from the generative model of Bayesian segmentation and then use it to train a CNN that hopefully can segment anything? And the fun part here is, can we actually do this with images that are synthetic, but they are not only synthetic, but also with completely random imaging parameters? This may sound a bit crazy. So the idea is, can we generate images that are so freaking diverse such that when we are shown a real scan, it's seeing like a particular case of this crazy distribution that we have down here. So we just take all this stuff, train a 3D CNN, and we call this like a Synth. This is mostly work by my PhD student, Benjamin. Of course, I'm the supervisor, so I get to take all the credit today. So just to make this clear, and this is for me the most important point of the whole talk, is like we have one neural network, we have one set of weights, there is no retraining, there is no nothing. Like, this is on FreeSurfer today. You can just go on FreeSurfer and say Synth input output, and you will get a segmentation. So I think in terms of like reproducibility, this is very important too, because like anybody is going to get the same result. There is no retraining, there is no fine tuning, there is no nothing. Whereas if you do any sort of like test time adaptations, yada, 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 it's gonna, the results are gonna change from site to site. So I'm gonna go a little bit more into the details of how this works. I'm gonna start with a simple example, which is generating a T1 scan. So you start from a segmentation, like I said. This segmentation during training, all you are saying is, well, just you have a bunch of this for training. No images, we only train on segmentations. The images we throw away. And you choose one label map from your training data set at random, pretty standard. We also do pretty standard spatial augmentation to artificially increase the diversity of our trained data set. Again, this is pretty standard. We composed an affine and a nonlinear transform. The affine is just rotation, scaling, shearing, and translation as usual. These parameters we pick from some random uniform distributions, and the limits of these parameters are set such that you don't do anything too crazy. So the rotations are plus minus 20 degrees, I believe. The scaling are between, I think, 0.85 and 1.15, something like that. And then for the nonlinear, we use stationary velocity fields that have the advantage of being diffeomorphic, meaning that you will not break the topology of your segmentation when you apply them to your scans. In short, what we do is we sample a low resolution stationary velocity field. We blow it up to the image resolution, so it's guaranteed to be smooth. And then we do the integration, which is pretty standard. So by doing that, you get your deform label map. Then you sample your Gaussian mixture model at 1 millimeter resolution. Again, this has a bunch of parameters, means and variances. We picked, in this case, the means and variances to resemble a T1. You don't have to, but this is what we did for this example. And then you just sample your Gaussian at every voxel. And once you've done that, the next step is simulating bias field. This is very important because we want to be able to analyze images without, like out of the box, without pre-processing or anything. We don't want to have to scroll strip, bias field correct, and so forth. The bias field we simulate almost the same way as the deformation. And once you've got that, we do a bit more of intensity augmentation, again, pretty standard, like random brightness and contrast differences, a bit of non-linearity, this gamma transform here. And then the last step is the partial volume model, right? We have to simulate some spacing, some thickness, and a target resolution. The target resolution will always use 1 millimeter, and the spacing and the thickness here, we made coronal 5-on-4. And this is pretty much it, really. We only do one more tiny thing. So this is the model, which is resampling back up to 1 millimeter isotropic. And the reason why we do that is so that the labels and the image live in the same voxel space. So it's very easy to train a convolutional neural network. Otherwise, it'd be a bit tricky, right? If they were in different resolutions, in different spaces. So yeah, this is what your trained data looks like. And this is the equation for the whole model, which is essentially multiplying all the conditional probabilities. We call this thing Synth RC because it's resolution and contrast specific. We don't use this in practice, but it's a useful baseline. More on this later. The next thing that you can do is to randomize the contrast. So you can play the same game, but now here in the Gaussian mixture model, these mean and variances, instead of like choosing them so they resemble a T1, we sample them from distributions such that every single time I get a different contrast. If you pay attention, you see it's a bit bananas, right? Like the left putamen or the left thalamus has a different contrast than the right thalamus, whatever. It's fine. Like the more you randomize, the better. And the equations are exactly the same, except for the fact that now you have these Gaussian mixture parameters that are sampled from this distribution. We call this Synth R because it's specific to resolution in this case. And then we have the full model, the full Synth model, which is we randomize everything. So we randomize the Gaussian mixture parameters, but we also randomize the resolution of the acquisition. So now what we're saying is, okay, we are simulating a slice thickness, which happens through Gaussian smoothing, with this kernel here with a standard deviation that is random, and then we resample with a spacing that is also random. So that's what you get. And again, the final equation is this one here, which again is just a product of all the conditional probabilities, and we add this distribution of the resolution parameters. And this is what we call Synth. This is what we have in FreeSurfer, the ultimate version of the model. A bit of like engineering tricks is that we use different versions of the label maps. The ones that with the whole head are the most detailed that we have, but every once in a while we drop the background. Sometimes we drop the CSF too. We do this to be able to support A, skull strip data, and B, ex vivo data. And then we also have versions that look the same, but they have like some white matter lesions. And this makes the method more robust against, for example, like multiple sclerosis lesions and so forth. In terms of morphological variability, we started from a data set that we have in the lab, which is the one that was used to build the atlas in FreeSurfer, and there is 40 of them. So it's not bad, but it's not a lot either. You can get like a better network if you also use segmentations from other data sets. So for example, you can use segmentations from HCP, like this one on the left, the Human Connectome Project, which is mostly young, healthy people. So you can see the tiny ventricles, but also from ADME, and that will make sure that it works better in cases with more atrophy. And the beauty of this is that, I mean, if you look at this or this, kind of like, we don't really, I mean, they're not perfect, right? And they have like little noisy speckles and segmentation mistakes and so forth. But the beauty of it is that we don't care, because remember that the image, like if you were doing supervised, this would be really bad, right? Like if your segmentation is wrong, you're throwing garbage into your during training, and therefore you're going to get garbage out at test time. But here, because the images are synthesized from these segmentations, they are perfectly aligned by construction. So you get away with quite a lot. So that's this, I mean, it helps massively to add all these like external cases from other data sets. And this is what the scans look like when you sample from this model. So you have like, these are axial slices. So some of them look crisp because they're axial acquisitions. Some of them look not so crisp. The contrasts are completely bananas. Every once in a while, you get something that resembles like a T1, sort of, but not really, like this guy over here. Yeah, but if you look at, I don't know, pairs of images, they look like crazy different. So the training part, I'm not going to go too deep into this. I don't find this particularly exciting. Like if you want to train this with a more sophisticated architecture, I'm glad to help you guys if anybody's interested. But we use like a very standard like 3D unit. So we start from 3D input labels, like I said. At every mini batch, you sample your image and the segmentation from your generative model, as you saw. We push this data to the 3D unit. You get your prediction. You compare the prediction to the ground truth, compute your dice loss, and you use it to backpropagate and train your unit. Like pretty standard. Again, if you want to replace this by a fancy new transformer, let me know. I'll be glad to, very glad to help you, so I don't have to do it myself. In terms of at test time, segmentation pretty standard too. You start from your scan, you resample to 1 by 1 by 1. Bear in mind that that's where we want the segmentation to, that's the space we want the segmentation to live in. You push it through your trained unit, you get a prediction, and then we figured we could squeeze like a couple of extra dice points, a bit more of performance by doing test time augmentation. So we take the image, we flip it left, right, we segment it, you get another set of predictions. You have to flip them back and reorder the slices. And yeah, you can average the two predictions and get your segmentation. So I'm going to show you some results. And we tried this because, I mean, the fun thing, right? The fun part is the whole, like, you know, being resilient against changes in contrast and resolution. So we use a lot of different data sets. So the first one is the one that I mentioned earlier, is the FreeSurfer, the data set that was used to train FreeSurfer. So we took 20 of the scans. There's 39 of them. That's why we call it T139. We took 20 of them for training, 3 for validation, and 16 for testing. We took 500 from the HCP and another 500 for ADME, just for training. And then for validation, we got a bunch of other scans. We got a bunch of T2s from an internal data set that we have. This FSM stands for Free Surfer Maintenance Grant. This is DAG grid, courtesy of DAG grids. At the DDS sequence as well. And then we also take these folks and generate low resolution versions just to have a bit of diversity in slice spacing and thickness from these folks. And at this time, what we do is to use a bunch of cases from this FSM dataset. So you have T1s, T2s, and DBS. We also have this T1 mix sequence, which we took 1,000 of those. So this is this was, I don't know how many years ago, but like our former coworker Mert Sabunju downloaded like every single T1 dataset that he found on the internet and combined them into like a zillion scans and processed them with FreeSurfer. So we took 1,000 of those, should be enough. We also have this small dataset that is it's small, it's only 8 scans, but it's useful because it's multispectral. So we have a T1, but also proton density scans. And we also took a couple of thousand flare scans from ADNI. So they're 5 millimeter axial. These are pretty interesting because in ADNI you also have the 1 millimeter MP ranges. So what you can do is to process the one mils with FreeSurfer and then use them as ground truth. It would be a silver standard for these folks. And we also find this small data set of CTs that had like these are 3 millimeter axial CTs that had corresponding MRIs. So we can play the same game and use the segmentation of the MRI as ground truth. And as competing methods, we use supervised networks trained on T1 scans. We use test time adaptation. This is the method I mentioned earlier, which is by the folks in ETH in Zurich. We tried our Bayesian segmentation tool, SAMSEG, which is available in FreeSurfer. Our method, Synth. And then, this is why I introduced them earlier, the resolution and contrast specific versions of Synth. So when we look at dice scores, and we start with the T1 baseline, as you can see, what's going on, right? Like if you train on T139 and test on T139, it's outstanding. It's over 0.90. It's almost as good as like manual segmentation. You're pushing the inter-rater variability at that point. When you try on other T1 datasets, there is a bit of a domain gap. Like I said earlier, there's different flavor to this T1 contrasts. So you lose 5, 6, 7 points of performance. That's what you see here. And of course, you cannot process other modalities with this network. So test time adaptation, a good thing is that it doesn't break anything in this domain, which is good. And it seems like on the T1 datasets, it does buy you a couple of points of performance, which is nice. And when you look at the other domains, sometimes it does a reasonable job. So it seems like in T2 and proton density, it's able to bring the network to a reasonable spot and give you like 0.80 dice, which is not amazing, but not terrible either. But in some other domains, it doesn't really work that well. SAMSEG is pretty good, strong performance across the board, always above 0.8, even if marginally for the proton density. But the problem is when you go to the low resolution data sets, it just falls apart. It really doesn't work. And Synth is pretty good across the whole board. So you get like, if you look at here at the T139 dataset, it's not as good as the fully supervised network. Still better than SAMSEG, but not as good as the neural network trained on the source domain, which is expected, but it's still 0.87, which is really good. But if you look at the other ones, it's about 0.85 almost everywhere. It's only for the flare and CT scans that it drops to 0.75, 0.80, but always like bear in mind that these are like 5 millimeter, 3 millimeters. I mean, this is a freaking CT scan, right? At 3 millimeter resolution. And this is like a 5 millimeter axial flare. So 0.8 is actually a pretty good dice score. And this is the interesting thing, or one of the interesting things, is what happens when you use the resolution specific network. So here we are training for the CT and the flare. We are training with like 3 and 5 millimeters respectively. It actually gets a bit worse, which you may or may not find surprising. Same thing with the specific resolution and contrast. So, I mean, this is consistent with converging evidence that with these neural networks that are so good at interpolating, but not so great at extrapolating, it is really helpful to simulate data that goes well beyond what's realistic. And it's also, again, supported by all this evidence from the domain randomization literature in robotics, where they play this type of games as well. So yeah, the idea is that by sampling contrasts that are so crazy to be real, you're essentially teaching the network not to rely on contrast at all, or resolution for that matter. Can show you a bunch of segmentations, see what it looks like. So this is the ground truth. This is like a 1 millimeter MP range from T139, so T1 mix, everything works essentially, right? The baseline test time adaptation, Samsec does a good job too, and Synth as well. It's more interesting when you have a flare, right? Like this is, or a DBS like this one here. So especially for the flare, which has lower resolution, this is like an axial flare from ADME, right? So now the test time adaptation, sometimes it works, but sometimes it doesn't. Like here you have like pretty terrible mistakes in the cortex upstairs, right? On the DBS, or these big mistakes as well on the flare. Samsec does a good job on the 1 millimeter scan up here on the FSM data, the DBS sequence, but struggles quite a bit with the lower resolution. Like for example, the pallidum is almost gone, or the cortex, the medial temporal lobe doesn't look great either. And Synth is surprisingly good at coping with the lower resolution. And like I said, it doesn't matter what resolution you throw in, you get a 1 by 1 by 1 millimeter segmentation. We tested this explicitly by taking 1 millimeter data and downsampling in different orientations, so coronal, axial, and sagittal. And you can segment these guys, and you get pretty much like good results everywhere. So you can use this to build plots of dice depending on resolution for different data sets and for different competing methods. And what happens here is when you have a supervised network, and I want to be clear, this is not a 1 millimeter network applied to 3 millimeter 5.7. This is like a 3 millimeter, 5 millimeter, and 7 millimeter network. Performance goes down, as you would expect, because you have less information. It's not magic. So you pay the price. And when you switch domains with flavors of T1s, you also pay a price in terms of domain gap. Now, when you look at Samsec, the proton density one we couldn't do with the T1 data, right? With the T1 network. But Samsec you can, and Samsec you are definitely paying quite a price in terms of resolution, particularly at 5.7 mil at pretty much every domain. And Synth brings you a bit of the best of both worlds. Like it doesn't, of course you pay a penalty when you go down in resolution. Like if we could get the same information from 7 millimeter data than 1 millimeter data, something would be wrong. But the slope, the rate at which you lose performance is much lower than for, say, Samsec. And funnily enough, when you look at the supervised networks, when you go to 5.7 mil, the gap closes. At 7 mil, like training with the real data doesn't really help you as much compared with Synth. But I think it's pretty cool that you stay above, like 0.80 everywhere for proton density T1 at 7 mil. So yeah, this made us very, very, very happy. But even also the T139, 31 scans. And yeah, this is for me. This little, let me point it there. Yeah, this is like pretty interesting. Some images of what things look like. This is how things fall apart or do not fall apart as increased resolution. The cortex looks smoother, as you can imagine, right? But like the rest of the brain looks pretty good at 7 mil. I'd like to show quickly this slide, just to give an idea of what the network is doing. So if you train your T1 network on your 1 millimeter MP radius, and you look at features, not in the beginning of the network, but like high-level features towards the end, they look like this, where you already see quite a lot of like structure up here or down here. And then if you take, say, like a low resolution T2 and push it through the same network, these features are completely different, as you would expect, because the network is not designed to cope with it. But with Synth, when you take like these two images from the same subject, right? One is T1, the other one is like downsample T2, and you push them through a network. The features look almost the same, which is, I mean, it's a bit smoother here if you pay attention in the cortex, but for the most part, it is pretty close. And the fun part, what did we do? We took this and we ran it on 10,000 scans from the packs, like pretty much no filter. And these are folks with memory complaints. So in principle, there should be no big strokes, tumors, or trauma. We did a simple automated QC. We did like, okay, we ruled out scans that had like MRA or DWI on the DICOM header, and anything giving like a total intracranial volume, like ICD under a liter, we threw away, we threw out, because it's mostly either a segmentation mistake or partial field of view. So like I said earlier, this is very easy to use. Free surfer, MRI Synth, -I input, -O output. So I encourage you to try. And we got like pretty aging curves like this using the this data in the wild from the packs. This is the cortical volume. This is the hippocampal volume. Your progressive nonlinear decline. And this is what you get. I'm not going to go into this today, but we have a robust version that I encourage you to try that kills, if you go back and forth, it will get rid of a lot of outliers. It makes the segmentation a bit smoother, but it never fails, essentially. And you can use this to look at other volumes as well, like, I don't know, the amygdala, or you have this pretty quadratic curve for the lateral ventricle. This is an easy one. The ventricle you could probably get with SAMSEC too. But I thought the amygdala looked pretty cool. And I'm going to quickly go over Synth-SR. It's going to be fast because it's essentially the same. The question is, can we, because Synth is good if you want to do segmentation, right? But could we generate, instead of a segmentation, a 1 millimeter isotropic MP range from a clinical scan? Because then you don't have to do segmentation. You can do whatever you want. You could do, I mean, I have no idea. You could do registration, right? Or any other analysis you want to do, or you want to segment with something like a different protocol with a different software. You have, for example, a package that segments the hypothalamus, and you want to run it on your clinical scans, right? So this is more versatile. We call it Synth-SR because it does super resolution, but also synthesis, and it's essentially the same freaking thing. The thing is that this is a very general framework, right? If you think about it, you start from your pool of label maps, which are isotropic. At every mini batch, you select one randomly, like we said. You randomly deform it, like we said earlier, same story. And now from here, you sample your Gaussian mixture model to get these synthetic high-resolution intensities. So it could be like T2S or T1S, or even multiple channels, I don't care. And then you simulate your artifacts and your resolution, and you get these synthetic low-resolution intensities, right? So what we were doing before was going from fake intensities to segmentation, either at high resolution or from low resolution here to high resolution here. This is Synth, what I have on the screen right now, right? You go from synthetic low resolution intensities to high resolution label map. But there's many other things you can do. You could do synthesis, learn how to go from T2 to T1, or you can do super resolution, how to go from low resolution T2 to high resolution T2. You can do both simultaneously. Or what we are doing here, which is learning how to go from the synthetic low resolution intensities to the original high resolution MP range that this segmentation was derived from. So I'm learning how to go from these guys over here, which are simulated and whatever contrast I want, to 1 millimeter MP ranges that I can essentially process with any software, any existing software, like anything works on 1 millimeter MP ranges. So like I said, I'm not going to go too deep into this, but we tried using it for pure super resolution first of T1s, and then processing with free surfer. So if you can use 1 millimeter as ground truth, we just generated 7 millimeter coronal, 5 millimeter, 3 millimeter push through free surfer, and especially the cortical segmentation falls apart. And after the super resolution, like you recover a lot of the high frequency details, and you get a nice free surfer segmentation. And yeah, long story short is that if you want to do, for example, hippocampal segmentation, like subcortical segmentation, or you want to do tensor-based morphometry, any sort of registration, you can get away with 5-7 millimeters, no problem. thanks to the super resolution. If you want to do cortical thickness, 3 is doable. Beyond that, it's not, as you can imagine, because you're looking for like much tinier changes there. And the fun part is, can we do it simultaneously with contrast synthesis and super resolution? So I can take a 1 millimeter MPRH, push it through free surfer, and this is my ground truth. I can take my flare, and then, of course, my 5 millimeter flare from ADNI. I cannot put this through, I mean, I'm not going to get, I cannot push this through free surfer and get the cortical analysis, but I can still put it through Samseg and get a segmentation that doesn't look that great at this resolution. But the other thing you can do is to use SynthSR and get a fake 1 millimeter MPRH, and then you can process with free surfer, no problem. And we did this in a control environment with a fixed number of sequences first, and we got some nice aging curves with expect effects. So we were happy about that. But we've done a bunch of things with this, maybe for another day, right? But like one cool application is hyperfine scans, like low field scans. So these are acquired with the hyperfine swoop, which is making a lot of noise in social media lately. So these are like 1.5 in plane 5 millimeter thick axial acquisitions. So I can take the T1 and or the T2 and convert them into 1 millimeter MPRHs. So these images are courtesy of Taylor Kimberly and Kevin Sheff from MGH and Yale, respectively. So this is the T2, there's the T1, and this is what SynthSR will do. So I can go back and forth. You can see there's a stroke there, stroke vision. And then these guys you can push through free surfer, and you can get pretty neat correlations with high field data. The cortex looks pretty good. White matter looks pretty good. The ventricles are a slam dunk, of course. Ventricles are always easy. The hippocampus is pretty good, which is I was very happy to see, because especially with an axial acquisition, the hippocampus can be tricky. The amygdala, not so much. This is probably the toughest one, right, at this resolution. But there is many other acquisitions that you can fit through this. I love this epimix sequence where you can get like all 5 contrasts in under 2 minutes at 1 by 1 by 3 with massive API distortion, as you can see. But hey, you get what you pay for. So same story here. We are turning like this is a flare T2, T1. You can turn into like a 1 millimeter MPRH, and you get like bias field correction along the way, because the images that we regress are bias field corrected. So that's a little bonus. But the fun part again is running this on the clinical data, right? I can take my contrast and resolution agnostic version. Again, this is already in free surfers. You can easily do MRI SynthSR, -I input, -O output, and get a fake MPRH, and then you can just run Recon all on it if you want. And you get pretty neat curves with your nonlinear effects for the white matter, which still goes up in the earlier years of the data that we have, which is from 20 to 90. And then goes down. The cortex goes down from the beginning, which we all know from the literature. This is a cortical gray matter, the ventricles with their characteristic square relationship, hippocampus, amygdala, thalamus, and so forth. So yeah, the key points of the talk is that these techniques, and we have some others coming, like we have a registration tool that is called Synth. We have, I'm working on age estimation, cortical surface placing, and so forth. And we're going to call them all Synth something to keep the branding. So they can process scans of any contrast and resolution without retraining, which I think will facilitate the adoption of these deep learning techniques in neuroimaging, which are not really widely adopted yet. And I think this is part of the problem. Also, Synth only requires segmentations as trained data. SynthSR requires images, but the segmentations don't have to be manual necessarily. And they can, if you simulate this during training, you can adapt to different levels of pre-processing. So they become robust to a huge range of variability. And again, like especially including atrophy and lesions, like Synth, we threw in, like I said, like all these cases from ADNI and HCP to make it more diverse. And yeah, the last message is that augmentation beyond realistic extents will get you a network that generalizes much better. And in terms of future work, Maybe we're thinking of exploiting images of the source domain to improve the accuracy, maybe doing this mix-up technique where you mix the data between synthetic and real scans. So maybe you can give a bit of like a more like realistic texture to your trained data, or maybe use adversaries. Everybody likes scans these days to try to improve the realism of the high resolution features in your images. Maybe improving the architecture. I'm not eager to do this myself, but if I find a volunteer, that'd be great. Maybe try transformers or EventNet. And improving the models of pathology. We have white matter lesions, but I really want to throw like tumors and strokes in there. And something that I really want to do is extending this to other problems like surface placement, registration as well, cortical registration. I'm also very interested in dissection photographs now, but that's for another day. And yeah, that's pretty much it. Of course, I need to acknowledge like all my collaborators. I must say in special like Benjamin Billo, my PhD student, he's done a fantastic job. And if you find this work interesting, he's actually coming to Boston. He's going to do a postdoc with Paulina Goland, so right to the left of him. So you can even meet him in person if you're around. And of course, the funding bodies, including the APSRC, the ERC, and the NIH. And that was it. Thank you very much for your attention. I'm going to leave the blatantly the publicity on the screen with the links. And if you just want to use the thing to try it, just install FreeSurfer, and it's super easy to use. If you want to train your own models, we have, of course, all the code on GitHub. So that's also possible.
Great. Thank you so much. That was super exciting. And yes, the answer to that first question is yes, I do want to test all of those things. I guess the first question, while I'm waiting to see if others will want to chime in as well, can you say anything about processing time? Again, a lot of us are used to what our usual, sort of FreeSurfer, I don't know, 24, 18 hours, some large number of time on your local computational systems.
Right.
Can you say anything about how the computational performance is on time?
Yeah. I try to be political in my presentations because I'm in the FreeSurfer lab, right? And I don't want and if I'm going to quote Doug Grieve, so it's like, no, the important thing is to get it right. It doesn't matter how long it takes. That is true, but at the same time, oh man, like FreeSurfer can be slow, right? These networks, they run it depends if you run on the CPU or on the GPU. If you have a GPU, processing a volume is approximately 2 seconds. We do, so for example, for Synth, we do a bit of post-processing in terms of like, filling the holes in the segmentation and a bit of this, a bit of that. And that takes maybe 15 seconds on the CPU. It's not easy to port to the GPU, like all these morphological operations, like filling holes and stuff like that. They're not that easily parallelizable. But if you switch that off, it's literally on the GPU, it's a couple of seconds per case. So that's an attractive point. And even without a GPU, if you have like a good machine, like TensorFlow and PyTorch, both of them, but they're really good at parallelizing if you have multiple cores. So if you have a box with, say, 16 cores, Synth will run in under a minute.
Cool, thank you. Any questions from the audience there? Courage to up. Great, go for it.
Hey.
Yes.
Thanks for a great talk. Can I ask you to speculate on how applicable this would be to gray matter lesions and tumors and strokes, as you say?
Yeah. So yes. So what we are doing right now, for Synth and well, it's kind of the same, but not really. So for Synth, we simulate the lesions, but we don't segment them. So you're saying, hey, I'm going to put like a bunch of lesions in mostly on the white matter, and then I'm going to learn to segment white matter everywhere. And for SynthSR, actually what I'm doing right now is I have lesions in the input, but I inpaint them in the output. So that SynthSR learns to inpaint the lesions such that the image that you get is amenable to being processed with anything. Like because
right.
Sometimes FreeSurfer will break if a lot of people do this, no? When they analyze images, they segment the lesions and they fill them in. So I give you the field thing directly. Now, if you want to segment the lesions, that can be a bit trickier. And we haven't tried that much, so I will speculate. And when we tried, if you just make the lesions another class and you say, oh, just segmenting, the problem is when you throw in images with lesions, it does great. But when you have images without lesions, it's very trigger happy. And I think, complete speculation, that if during training, when you feed images without lesions, you heavily penalize, segmenting lesions anywhere, you could fix that. Because if you use these dice scores during training,
Right.
what happens is that if you have no lesions at all, the dice is 0, no matter what you do. I mean, if you put a lot of lesions in the white matter, the dice of the white matter will go down, but that's not a high, it's not such a big price to pay. So I think the way to go would be to say, hey, when I show you a scan without lesions, let's say that you penalize the lesion volume multiplied by a number. So every pixel you label as lesion, you have to pay for. So
Right.
I'd love to try that. I just don't have the time or the bandwidth. But
so what if you would have lesions manually labeled, but you wanted to ultimately use the data to do surface-based stuff? So where you're running into the issue that free surfer will break if there's a lesion because it can't, process, it can't reconstruct it and segment it.
Mm-hmm. I think you're more familiar than me with this problem. I thought that people did lesion filling for this matter, right?
Yeah, they do, but I don't think it always works.
Yeah, so what I would, again, speculate here. So this is very, very preliminary, but Andrew Hoops from our lab is working on deep learning surface placement. And I think something that he needs to try at some point is precisely this. It's like learning to place surfaces in presence of lesions, which you can definitely do. And you would hope that a neural network can learn to be robust against this.
Okay, thanks.
Sorry.
I see a Satra question.
Hey, Eugenio. Thanks a lot for the talk.
Yeah, thanks for the invite. Yeah.
I have a quick, maybe a little more philosophical question on these networks. Does it learn anything about the brain or structure of the brain?
Oh, absolutely, right? I mean, it has to. I mean, you only if you're throwing away the contrast and you're throwing away the resolution, right? All you have left is anatomy.
So in that sense, could I flip it around and say, can you do anomaly detection for the kinds of things that Dorit was perhaps talking about?
I've tried this. So something that you can do, right, is once you have, say, segmented or run Synthesart or wherever, or run both, I normally run both one after the other. You can look at the deviations from the Gaussian model. So I can take, for example, the white matter, and I can take compute robust statistics. So a very simple way would be I could take the median as an estimate for the robust mean. And I could take the median absolute deviation. There is a factor there to get the standard deviation. I think it's like the golden ratio or something. So the median absolute deviation multiplied by 1.48, I think, gives you a robust estimate of the standard deviation. And then you can compute z-scores and look at that. But it's a pretty simple. It's a pretty simple model, right? Something more sophisticated. I don't know. I haven't thought of that. Maybe.
So, since you have access to the MGH database, one of the thought processes is there are things with meningiomas, right, which are very different from your standard tumors or other things, and would require kind of an understanding of the model or the brain that this is really an anomaly in a different sense than just kind of changes of texture. It's not a horse to a zebra, but a horse with an additional backpack.
Yeah. An additional leg, maybe. Right. So the robust, I didn't go into this, the robust version of SynthSeg, what it does is that it runs SynthSeg first with only 4 classes, like a simplified tissue model. Then it pushes it through an out. So that segmentation sometimes breaks. Sometimes it has holes. Sometimes it has topological problems. But we push that through an autoencoder that gives you like a topologically correct version. Too smooth normally, but correct. And then we use that as a prior for a second synth with all the labels. So I'm wondering if the autoencoder can be used for this in some, I don't know.
Would be fun to chat
It'd
because
be fine. Yeah. I have no idea, honestly. Sorry.
Okay, we're coming up on the edge of the hour. Appreciate everyone's attendance. Any more burning questions? Otherwise, we can always carry on the conversation, as we proceed, going forward. Again, I want to thank you again for the presentation and remind everyone that next month, June 3rd, we will have another special guest from our collection of collaborative projects. It'll be Ted Satterthwaite from UPenn, presumably talking about developmental trajectories of some sort, but we'll let him tell us next month.